Okay, so last class we talked about, uh, you know, we talked about some few basic laws that we will need, at least their basic abstract forms that we will need for quantum computing, or what we are going to study about them. And then we also define, or kind of looked at polarizing filters. Right, so these were devices which are very similar to measurement devices, but kind of function a little, they have some physics behind it. So they would convert one of the measurement outcomes into heat. Okay. And they already had some somewhat surprising properties in that you stack two of them, maybe no light goes through. I put an additional barrier by placing another filter in between, and suddenly light starts going through. Right? That was a little bit counterintuitive. And much more counterintuitively, we saw how we can play the game of the EV bomb, right? So this was kind of a very quantum phenomena, and I'll say a few words about that again. Okay. So today, what we will do is kind of look at the general forms of the basic laws that we need, and then start talking about quantum gates and multi-qubit systems. Okay, so both of these are very important. All right, we'll do without the class microphone today, as I am out of batteries. Let me try this other pair. Okay. All right. And before going on, a few important announcements. First, homework 6 will be out today. And we will have an earlier deadline for this so that I can release the solutions for you to review before the next exam. So this is due December 6th at 10 p.m. Okay, so keep that in mind. So it's 2 days earlier than usual. And this is so that you have time to review them for the exam. And exam 2 is now graded. And the mean was 84%. Max was 100%. Median is about the same. Okay, so all kind of, very similar to what we had for exam 1 and also the previous years. Any questions about the grading? If you have any regrade requests, please submit them promptly so that the TS can handle them. Okay, and we will have exam 3 on December 9th from 8 a.m. to 10 a.m. to 10 a.m. And this is per university schedule, and this is in Kaplan Hall A51. Okay, and this only covers the last 6 lectures. So lectures 15 to 20. Sorry, 14 to 20. Okay, so basically context-free grammars plus quantum path. Okay. And for the exam, we will grade them, the TS will grade them as soon as possible. And once they grade them, I will release the release course on Gradescope. And you will have two days to submit regrade requests. Okay, so once the scores are released, you'll have 2 days before for you to submit any regrade request. We can't do multi-round. We don't have time for that. But after that, I'll just assign the grades. Okay. Any questions about the logistics? All good? Okay. All right. So with that, we can now continue with our lectures. So, we were playing with this game, right? So there's an adversary who happens to be a physicist, and okay. So this was the EV bomb scenario. We're given a box. We don't know if it has a bomb in it, bomb or that. Okay. We were trying to detect which of the two cases we are in, and naturally while minimizing the chance of explosion. Okay. And the surprising thing that we saw is that there's a simple, to describe experiment where you take your box, no matter what it is, you put a tiny rotation device okay. We send a photon in, goes through, and then we cycle it back. Okay. So we repeat this process some number of times, and then we do a measurement. Okay. So this was the experiment that we came up with after multiple trials. And this has this remarkable property that we can basically drive down the chance of an explosion to as close to zero as we want. We might just have to loop a little bit longer, but essentially we are minimizing the chance of explosion as much as we want. Okay? So for example, if we run the cycle 90 times with a 1-degree rotation device, chance of explosion, the total chance is only 0.0036. Okay, it's a very tiny chance that we will explode, and whenever we don't explode, we know for sure what case we're in. Okay, and as I mentioned last lecture, this is not possible if you don't have quantum rules. Okay. If it was a classical filter, or you don't have access to qubits or these rotation devices, you cannot do this. Okay. Any questions about this experiment? I say this is a somewhat of a computational task, albeit for a toy problem, but it shows a case where the laws of quantum mechanics allow you to do something which is not possible otherwise in a computational sense. Okay. no matter what you do without the rules of quantum mechanics, no matter how many times you use the box, you wouldn't be able to get such a trade-off between the chance of explosion and chance of detection. Okay? And there are lots of other problems where we know such separations, especially when you have to interact with some object in a black box way. Okay? So that's kind of it shows up in other quantum computing classes, but we won't be touching on those things. Okay. All right. Now that we're done with this sort of demonstration of the additional power we might get from quantum laws for computational reasons, let us see if we can actually do something useful with it. Okay. It's not like we want to solve EV bomb problems every day, right? We would like you do more useful computational things, and that's what we're going to talk about. Okay. So to do that, let us go back to the laws of quantum mechanics, and we're going to generalize them a little bit. Okay. Let's see if I can copy them. Okay, so these were our old laws. If your system could be in one of two possible states, it could also be in a superposition, and the superposition is dictated by this alpha and beta, right? And then we have these measurement devices and so on and so forth. Okay, and we also had the third law. Which told us that we can build devices. Nature gives us the ability, for whatever reason, to build devices to rotate the state or reflect if you want to, and also to get this general measurement devices. Okay, these are the only things that we could do on a single qubit. All right, and also we had this picture that a qubit is basically a photon for us, and we would denote it as alpha times 0 plus beta times 1. We could view it as a point on a circle, on the unit circle. Okay? But at some point, we have to outgrow these diagrams and start using math for them. And the right math for talking about states and quantum computing is vectors. Right? So we can think of 0 as basically being a vector, which is 1 and 0, and 1 is 0 and 1. Okay? So we can think of a qubit as basically a two-dimensional vector with real valued entries, right? So a single qubit is a 2D vector. Okay? And of course, there's a constraint on this alpha and beta. So a vector with 2 coordinates. Okay? And with the constraint that the sum of squares of the entries is exactly 1. Right? So this is all well and good. It's kind of complete when you're dealing with a single qubit, a single photon, right? But there's not much computation you can do with a single qubit. You have to deal with multiple qubits, right? If you're only working with one bit at a time, there's no interesting computational problem that you would really solve. So to talk about multi-qubit state systems and And then to circuits, we need to generalize whatever we studied for single qubit to, to allow more states. Okay. So the generalization of the first law is very similar. Okay. So here, we said if a system can be in one of two options, it can also be in the superposition of these options. In the general case, it's essentially the same. You say if it can be in one of D options, whatever the D is, maybe D is 4, D is 8, D is 16, 24, whatever you have, then it can also be in their superposition. Okay? And we'll denote these options as 1, 2, 3, and so on. Okay? Then the state psi is of the form okay. So if it can be in one of D options, it can also be in the superposition of these things. And you have the same constraint as before. So alpha 1 times 1 plus alpha 2 times 2 and so on. Except now, all of the sum of squares, sum of all of the squares should be 1. Okay? And these alpha i's are called amplitudes in physics. Okay? So one way to think about it, it's helpful, at least in the beginning, to gain some intuition, to view it as saying my state is with amplitude alpha 1 in 1, amplitude alpha 2 in 2, amplitude alpha 3 in 3, and so on. Okay. So the analogy to keep in mind is a little bit like saying it's probability something, probability P1 in state 1, probability P2 in state 2, and so on. That's not quite right, because these numbers alpha i's can be negative as well, right? And that's important. Without negative numbers, there is no quantum advantage. So they can be negative as well, but you can think of it as with amplitude alpha 1, it's in 1, amplitude alpha 2, it's in 2, and so on. Okay. So and you can also geometrically view it as just as a single qubit corresponded to a point on the unit circle. If you have more options, you can think of it as a point on a higher dimensional unit sphere, or as a vector with d coordinates, alpha 1, alpha 2, so on, to alpha d. We'll think of it as a column vector where the length is 1, right? So the length is basically the sum of squares of everything. Okay. All right. Any questions? Okay. Just to be concrete, the state 1, for example, corresponds to the vector 1 with all zeros. The state 2 corresponds to the vector 0 and 1 and all zeros, and so on. Okay? Because it has amplitude 1 with 1 and 0 everywhere else, and so on and so forth. Okay. And finally, so this is for just first law. How about the second law? What do you think? What would be a natural sort of extension of the second law when you have more than two options? Okay. As I said, nature gave us lemons, but after that, it's pretty kind. Everything kind of extends in a natural way. There are no further twists. So what would be an extension of this to multiple possible states? Yeah, exactly. Right. So we can have uh, I can build a measurement device for these vectors 1, 2 up to D, and I'm going to write it this way. So it has, so I can build a measurement device such that whenever I send this state, which is in one of D possible options in, I get 1 with probability alpha 1 squared, 2 with probability alpha 2 squared, so on with probability alpha D squared. Okay, kind of straightforward extension of what we had when we only had 2 possible states. Okay, but you have the same non-trivial thing here, non-trivial physical restriction, and on how we are able to access the state. Whenever I make my state go through this measurement device, it changes the state. I cannot just check alpha 1 without changing the state. I send it through this measurement device. I get the state, which is collapsed to one of the basis vectors, 1, 2, all the way up to D. Each one happens with a corresponding probability. Okay? Any questions? All right. Now, we also had law 3C. Okay. For any 2 perpendicular vectors, I could build a UV device corresponding to it. What would be an extension of that when I have multiple options? Any guesses? As I said, you don't have to, there are no twists here. The natural thing would work. So what would be the natural extension of this when I have, let's say, 3 possible states or 4 possible states? So for any 2 perpendicular vectors, I could build a measurement device earlier. Now, for any D perpendicular vectors, let me call them U1, U2, all the way up to UD. We can build a corresponding measurement device. Okay? So I can take any set of perpendicular vectors, D of them, so that they form a basis for the D-dimensional space that we are sitting in. Okay? And I can build a device which measures with respect to that, right? So just as for the case of 1 through D, whenever I send it through this measurement device, the state is going to collapse into one of these options. It's going to be U1 with some probability, U2 with another probability, all the way up to UD. Okay? So it is going to collapse into one of these D possible options. Right? And the probabilities are going to be what? Okay. So again, nature gave us these probabilities could have been much weirder, much more complicated to compute. But it turns out that they form a very simple equation. Okay. The probability that I would see U1 is basically the length of my state psi when projected onto the direction U1. Okay. So, imagine these are my high dimensional vectors. This is my U1. This is my psi. They both have the same length. Their length is exactly 1. The chance of seeing U1 is the square of the length of the projection. Okay? And mathematically, it's actually convenient to write this as this way. I'll define this in a second. Okay? So the dot product between two vectors psi and u is denoted as kind of the flip of the bracket followed by the original vector. Okay, this is quantum notation for dot product between two vectors. And the definition is, I have a vector x which has d coordinates. So let's say something like this. And I have another vector, let's say y, which has d coordinates again. Then the dot product between them, x slash y, which is called bracket. Okay. And this is x1, y1 plus x2, y2 plus all the way up to xd, yd. Okay. You have two vectors. The probability of seeing psi, when you measure psi in this U1 through UD device, the probability of seeing that is exactly the dot product square. The square is important, so I should put that in. Okay. And what's the definition of the dot product? You align them coordinate by coordinate, multiply the coordinates, and add them up. Okay. And why this loss? Why do we have this dot product squared and so on? Really, we can't argue much about them, as Feynman famously told his students. Okay, so why are these probabilities this way? We are not very sure, but we can calculate with that. Okay, so let's do some examples to see what happens, right? So what is this saying? I can have a very complicated d-dimensional or d-state system and some weird basis under which I'm building the measurement device. But calculating the outcomes of each event, the probability of each event is, is a simple formula, kind of a mysterious but simple formula. You compute the dot product, you take the square. You compute the dot product, you take the square. That's how you get all of the probabilities. Okay? So for example, let's say I take my basis to be okay. We can think of these as vectors, right? So this is the vector where the 2D vector, which has 1 over square root 2 and 1 over square root 2, minus is also a two-dimensional vector where I have 1 over square root 2 and minus 1 over square root 2. Okay? And this is my u, let's say, and this is my v. They are perpendicular to each other. So I can build a UV device for them. Right? So let me call this the plus minus device. Right? And let's say I send in a single photon, psi, which is maybe 0.8 times 0 minus 0.6 times 1. I'm going to get a photon again out of it. Right? But what state is it going to be in? Because it's a plus minus measurement device, it can only be in those two options. Right? It's either a plus or a minus. Okay? Now, what's the probability that I see a plus? It's not clear, but I have a formula for calculating it. All right? And there is no avoiding these formulaic calculations. To compute this probability, I need to compute the dot product between my state and the corresponding perpendicular vectors. Right? This is basically, as I said, you need to align. I can think of this, my state, as a vector which has 0.8 and minus 0.6. Okay? And by the formula, I need to align these two things and compute the product. So it's 0.8 times 1 over square root 2 plus minus 0.6 times minus 1 over square root 2, which is 0.2 divided by square root. Oh no, sorry. Which is 1.4 divided by square root 2. Okay? Right? So the probability of seeing plus is 1.4 whole square divided by 2. Yeah? Oh, sorry, you're right. Yeah, this should be minus. Yeah, because I put a minus here, this is minus. So yeah, this is 1.4 whole squared divided by 2. And with the plus, it would be 0.8 times 1 over square root 2 plus minus 0.6 times 1 over square root 2, which is 0.2 divided by square root 2. Okay? So this guy is any questions? Okay, so given any description of the vectors which define the measurement device and the state, I can compute the probabilities of the different outcomes. Okay, and they follow this dot product rules. There is no going around computing these things if you want to do quantum computing. All right, any questions about them? And this would extend to D, whenever I have 3 possible states, 4 possible states, and so on. Okay, and just sometimes some calculations are particularly easy. For example, if U and V are perpendicular, then their dot product is 0, right? It's basically saying that the vectors are perpendicular is equivalent to saying that the dot product is 0. Okay? All right. And lastly, we kind of have all of the extensions for the laws that we had for a single qubit, except for this rotation and reflection. Okay. This one is a little bit non-trivial to guess. Okay. I would say 1 and 2, extending them to d bits was, 1 was, okay, it should be in the superposition of all d possible things. Sum of squares should be 1. That seemed like a natural extension. Okay. 2 also was somewhat natural. Like the first part, saying that for any d perpendicular vectors, I can build a measurement device, that's a bit natural. But then the actual formula for the probabilities, okay, we got lucky. I would say we got lucky. It's not some complicated square roots, cosines, sines, whatever. It's a simple dot product. Simple in the sense that you give me the vector descriptions, I can actually compute them. It's an easier computation than using high school trigonometry, even if you're working with single qubits. Okay, in that sense, we got lucky, I would say. The third one is more non-trivial to guess. Okay, and there's a lot of hidden magic behind this third law. And that underlies much of quantum physics, I would say, and quantum mechanics, quantum computing, and many, many, many other fundamental things that we take for granted. Okay, and this categorizes what are gates or transformation devices. Okay, and I'm going to state it. If you haven't seen linear algebra, then it might not make much sense, as stated. But we will see examples that we would need to define quantum circuits later on. Okay. Nature, in all of its generosity, allows us any kind of transformation device which is linear. Okay? Meaning, so earlier we were doing rotation, we were doing reflection, and so on, right? Now it's going to allow me, it allows me any transformation, any way to map one state to another, as long as it has two conditions. It satisfies two conditions. One, it must be a linear transformation, meaning if I, let's say, do actually, let me not use size, let me use x because that can be a little bit confusing. Okay, so it's a linear transformation. That's number one. And it must preserve length. That is, for any vector x, ux has the same length as x. Okay, so this condition makes a lot of sense, right? Or at least, makes things much simpler, because states have a strong constraint on their length. The sum of squares of the entries should be 1. If you put them as vectors, they must lie on the high dimensional unit sphere. They must be at most exactly distance 1 from the origin. Okay, as long as I take any transformation which is linear and preserves length, nature allows me a device which can make that transformation. There exists a device which can do this transformation. Okay? We can build a device which takes as input psi and gives u times psi. Preserves length. We can build a device to do psi to u of psi. Okay? Any questions about this, really significant generalization? We'll see examples to make more sense in a little bit. Yeah? It has to preserve dimension by definition because we are always going from d dimensions to d dimensions. Okay? Any other questions? Okay, so let's do some examples. So where are we going with this, right? So eventually, in a few, let's say in next 20 or 30 minutes, we'll basically say what multiple qubit systems are. They will be systems which can be in superposition of many states. And then we had AND gate, NOT gate, OR gate, and so on, right? We will introduce gates similar to those, but those work in the quantum world, okay? But there's an important constraint. Gates in the quantum world have to preserve length. I cannot just realize I cannot have an AND gate, for example, in the quantum world directly. I have to do something because it has to preserve length. Okay, we'll talk about that. So that's where this 3a, 3b, this law is going to play an important role. Not because it's something that we like, because that's what nature gave us, and we're going to try and do something with it. Okay? So let's talk about the first gate. And the first gate, the simplest one to think about, is going to be the NOT gate. Okay? Okay. And so what's a quantum NOT gate? Okay. So I'm going to first write down the formula for what a quantum NOT gate is, and then we will try and kind of figure it out from first principles based on the laws. Okay. So a quantum NOT gate, if I send in a state which is alpha times 0 plus beta times 1, I'm going to get a state again, a photon, in some state. But what is this new state? Any guesses? Take your first guess. As I said, after the laws, nature starts being kind to us in that once you accept them, everything is logical. What happened here? So what should the output of the, quantum NOT gate be? Yeah?
Beta 0 alpha.
Exactly. Okay, now let me ask you, why did you take this particular guess? The opposite, right? In some sense, not should flip the state in some sense. Okay? So, in other words, if I send in something in state which is alpha and beta, I'm getting beta and alpha. Okay? And let's do some sanity checks to make sure this is consistent with the laws of physics as we know it. At some point, we'll just start doing the vector representation, but we can work with all of these things, right? So how would one arrive at this particular guess? Let me break it down. So naught of 0 should be what? Naturally, it should flip a 0 to a 1. That's what it does in the classical world. Okay? So if I want to talk about quantum NOT gate, I would expect naught of 0 to be 1. Right? So in other words, if this is in vector representation, naught of having a 1 in the first coordinate and 0 in the second coordinate should become 0 and 1. Okay? Naught of 1 equals 0. Again, this is extrapolating from the classical notion of a NOT gate. If I send in a 0, I get a 1. If I send in a 1, I get a 0. Right? And we know, or we are restricted really, from quantum QM law 3 that any transformation, any gate that you can realize in the physical world must be a linear transformation. Okay? So meaning, if I know what happens on 0 and what happens on 1, then it completely determines what the gate is going to do on every other state. Okay? I can't say 0 goes to 1, 1 goes to 0, but then 1 over square root 2, 0, 1 over square root to 1 goes to 1 over square root to 0. Or anything. I cannot do any of those things. Okay? So, for example, if U is a linear transformation, let me say it more in a better way. What should this be? Well, any gate is a linear transformation, and a linear transformation, when applied to the sum of inputs, becomes sum of the individual applications. Right? That's the definition of linear transformation. Okay? So this is enough to tell us that naught of alpha times 0 plus beta times 1 is alpha times naught of 0 plus beta times naught of 1, which is alpha times 1 plus beta times 0. Okay? So this is how you would guess, arrive at the formula for quantum NOT gate. You know what it's supposed to do on 0 and 1, but by QM law 3, any transformation, any gate that you can realize in the physical world must be a linear transformation. Right? Once I know these two things, I know what the gate is going to do on every other input. Any question about this? Okay? All right. So let me put that down because that's an important principle in designing quantum circuits. If we know how a gate transforms on a basis, we can extend it to all states. Okay? This linearity is really, really subtle and quite different from classical computing. It seems bizarrely restrictive. Okay? And it is restrictive, but we will see how to exploit it. Okay? All right. So we have our first gate, the NOT gate, and let's make sure that it checks all of the boxes of being physically realizable. Right? So for a gate to be physically realizable, it must be a linear transformation. We know that. That's how we arrived at the formula even. And it must preserve length. Right? And as we defined it, naught is preserving length. Alpha beta goes to beta alpha. So alpha squared plus beta squared, if it was 1 before, it is 1 afterward as well. So at least theoretically, I can build the laws of quantum mechanics, the laws of physics, allow me to build a device which can implement the quantum NOT gate. Okay? All right. Next, we arrive at perhaps the most important quantum gate, which is called the Hadamard gate. Why is it called the Hadamard gate? That's a very interesting but a very different story that we won't touch upon. But it's a gate which corresponds to the following operation. And we will denote it with the H. Okay. I'm going to write down the linear algebraic view of the gate and then kind of a pictorial view of what the gate is supposed to do. All right. So what's the linear algebraic way? Once again, I'm going to use the fact that every transformation is a linear transformation. Anything realizable in the quantum world must be a linear transformation. So if I tell you what the gate does on 0 and what it does on 1, I'm good. Okay. So what does it do on 1, on 0? It transforms a 0 into a plus. It transforms a 1 into a minus. Okay? All right? Now, once I know these two things, I can, of course, write down what it does on any generic state. If I send in alpha times 0 plus beta times 1, I get alpha times h of 0 plus beta times h of 1, which is alpha times 1 over square root 2 plus okay. If I gather the 0 terms, I get alpha plus beta over square root 2 times 0 plus alpha minus beta over square root 2 times. Okay. So the way the Hadamard gate transforms inputs is h of alpha times 0 plus beta times 1 equals alpha plus beta by square root 2 times 0 plus alpha minus beta by square root 2 times 1. Okay. If I think of it as vectors, alpha and beta goes to alpha plus beta by square root 2, alpha minus beta by square root 2. Okay. All right. Now, once again, let's make sure that we are not running afoul of the laws of physics, right? If this is a gate that we can actually build in the real world, it must satisfy that it is linear. Well, it is going to be linear because that's how I'm kind of defining it. I define what it does on 0 and 1, and then for every alpha and beta, I use linearity to define it. So that part is fine. We have to check that it preserves length. We can check that. Right, so what is the length of this vector? Alpha plus beta by square root 2 whole squared plus alpha minus beta by square root 2 whole square, which is 1 over 2 times okay. Lo and behold, it is also preserving lengths as we had required. Okay. Any questions about this? Okay. There's also a geometric way of picturing what the Hadamard gate does. So let me draw that. It's helpful, when you're dealing with 1 or 2 qubit things, but afterward, there's no way around using linear algebra. So the way we defined it, the state 0 goes into plus, right? And the state 1 goes to minus. Maybe let me draw it this way. Okay, 0 goes to plus, 1 goes to minus. Okay. And if you squint at it at the right angle, you can see that the Hadamard gate basically corresponds to reflection about the line at an angle of 22.5 degrees. Okay. If I draw a line at the angle 22.5 degrees and my transformation is reflect about this line, that is exactly the Hadamard gate. Okay. So one of the most important gates in quantum computing, in fact, besides the classical ones, this is the only one that you need to get all of the power of a quantum computer. Sounds kind of so benign, right? I just need to be able to reflect about 122.5 degree angle, but the power comes from linearity, as we will see. Okay. Any questions about the definition of these two gates? We will see more gates and more examples because it's a little bit counterintuitive where the subtleties are. Okay. All right, let's take a 5-minute break. When we come back, we will talk about other gates, especially those that operate on multiple qubits. Started again. Okay, so as I said, there are many different ways of describing quantum gates. You can think of it as one is tell me what the gate does on a basis and extend by linearity. The simplest way to describe a quantum gate, especially if it's a single qubit gate, is to, draw or describe as a rotation or a reflection. Okay, so this is the simplest way to describe a quantum gate for a single qubit system. Okay, the second, more refined way is to tell you what the gate does on a basis. Tell me what it does on 0, tell me what it does as 1, then I know what it will do on any other state. Okay? But the real way, so let's say, maybe this is how you would teach quantum computing if you're teaching to, let's say, a high school or maybe a middle school kid. This is for high school. But the real way to talk about a quantum gate is through matrices. Okay? To write down the matrix corresponding to the gate. Okay, and this is like undergrad. Okay, that's my caricature anyway. Okay, so what do I mean by this? Let's think about the NOT gate. Okay, let me call it the Q NOT gate just to distinguish it from the usual NOT gate. So we have the quantum NOT gate. Okay, and if I send in alpha and beta, I got beta and alpha, right? So alpha times 0 plus beta times 1 became beta times 0 plus alpha times 1, right? And if I were to think of it as a geometric operation, what does it correspond to? And what kind of reflection or rotation is it? So, what happened? A 0 became a 1, and a 1 became a 0. Yeah? Reflection across a 45-degree angle, right? So in some sense, the NOT gate is basically reflection across the 45-degree angle. Okay? This is kind of, the simplest way to describe it. You take a state, you reflect it across the 45-degree angle, you get the output state, right? And you can also define it by this sort of vector operation. 0 goes to 1, 1 goes to 0, and then we can extend it to everything by linearity. Right? But what's the matrix way of viewing it? So remember, every quantum gate, every transformation that you can realize in the physical world corresponds to a linear transformation. Why? I don't know. Nature somehow likes linearity. It's kind of weird if you think about it. It is genuinely weird to me. But nature likes linearity, right? So, how do you describe linear transformations? Yeah? Matrix, right? So, every linear transformation actually corresponds to a matrix vector multiplication. So all of quantum computing is just linear transformation, it's just multiplication by matrices. Okay? So for example, for the NOT, I send alpha times beta to beta times alpha. Okay? So if I want to picture it, I want a matrix a 2 by 2 matrix such that I get this. So every quantum gate, and as we will see, every quantum circuit corresponds to a matrix. There will be additional constraints on the matrix, but first it corresponds to a matrix vector multiplication. It has to be linear. There is no way around it. As I said, nature somehow likes linearity. Okay? But what linear transformation or what matrix vector multiplication would convert alpha beta to beta alpha? Yeah? 0, 1, 1, 0. Once I write it down, you can check, right? So here, for instance, if I do 0, 1 times this one, I get beta. If I do 1, 0 times alpha beta, I get alpha. So this is true. Okay? So a Q naught gate is really just the matrix 0, 1, 1, 0. Okay? You might wonder how you would get this. There's also a formula for kind of getting at the, going between the different views. For instance, if I know how the Q naught gate operates on 0, that will be the first column. How it operates on 1, that will be the second column, and so forth. Okay? Any questions about this? All right. So this is what the Q naught gate is. Now, what is the Hadamard gate? So remember, what does the Hadamard gate do? It takes alpha and beta and it has to be a 2 by 2 matrix. The output is alpha plus beta divided by square root 2, alpha minus beta divided by square root 2. Okay, and as we said, naught is reflection about the 45-degree angle. Hadamard is reflection about the 22.5-degree angle. Right, kind of a small difference, but big difference in making these things physically. Okay, all right. So what is the matrix corresponding to the Hadamard gate? Any guesses? Yeah. One over square root 2 and 1 over square root 2 minus 1 over square root 2. Okay, so you can check once again. Once I have the matrix, I can check if the equality holds. This times alpha beta, I get alpha plus beta by square root 2. This times alpha beta, I get alpha minus beta by square root 2. Okay, another way to kind of arrive at it is the first column should be what happens under the gate on 0. We got plus, right? That was the definition of Hadamard. So I should get 1 over square root 2, 1 over square root 2. Here I will get 1 over square root 2 minus 1 over square root 2. Okay? So this would, be the 2 by 2 matrix, which has 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2. Okay? If you're familiar with the term, every quantum gate, especially as we are talking about it with only real numbers, corresponds to an orthonormal matrix. Must be a matrix, first of all, and the matrix also must have some special property that the columns are all perpendicular to each other. Okay? We won't be using that, but that's something to keep in mind. All right? So now let's extend to more powerful gates and then to quantum circuits. So we have 3 different views, but we will drop one of them very quickly because I cannot really draw pictures in more than 2 dimensions. If I have 2 qubits, I have 4 possible states. I can't draw a 4-dimensional sphere, at least not yet. All right. So we are going to stick to these 2 descriptions, 1 and 2. I'll tell you what the gate does on basis vectors, and then we can extend it to all possible gates by all possible states by linearity, right? And of course, the more compact, the more precise way, I shouldn't say precise, but more compact way is to write down the matrix for it. Okay? All right. The first multi-qubit system is, first I need to tell you what a multi-qubit system is. Okay? And I'm going to be a little bit not fully rigorous here. If I want to be fully rigorous, then it's going to be a little bit tedious. So, there'll be some gaps, but the gaps are benign, right? So bear with me for that for now. Okay. So I have a 2-qubit system. We will think of it as 2 photons. Okay. A single photon can be in either 0 or 1, right? And then a superposition of those. If I have a 2-qubit system, how many possibilities do you imagine? Again, we are going to use our heuristics first, and somehow nature is consistent with them, right? So if I have 2 bits, 2 classical bits, how many options would I have? I would have 4 options. First one could be 0 or 1, the second could be 0 or 1, and hence I would have 0, 0, 0, 1, 1, 0, 1, 1. Okay? The same for a 2-qubit system. So a 2-qubit system is like a quantum system where I have 4 possible options, right? So I have 0, 0, 1, 0, 0, 1, 1, 1, right? But then the state can be any superposition of these 4 things, right? Say 2-qubit system is of the form, I'm going to write it as alpha 0, 0 times 0, 0 plus alpha 1, 0 times 1, 0 plus alpha 0, 1 times 0, 1 plus 1, 1 times 1, 1. Okay? And of course, we always have the length constraint. These can be negative numbers, but their sum of squares should be 1. Okay? Any questions about this? A 2-qubit system has 4 options. To describe it, I need to write down 4 numbers. I cannot even write them down often, but if I were to write it down fully, I need to write down 4 numbers. Okay? All right, that's fine. How about a 3-qubit system? Oof. Okay, let me just draw from scratch. So 3 qubits would be, I have 3 photons. Okay, and how many possibilities will I have? I'll have 8 possibilities, right? 0, 0, 0, 0, 0, 1, and so on and so forth. Okay? So I'll have 0, 0, 0. Let me write as maybe 1, 0, 0, and then 0, 1, 0, and then 1, 1, 0, and then okay. And a 3-qubit state will be a sum of all of these things. Okay, and once again, we'll have the sum of squares. Okay, all right. So you can already see something non-trivial happening in that to describe a 3-qubit system, you need 8 numbers, right? If I have a 10-qubit system, I would need 2 to the 10 numbers, right? So in some sense, there is some exponential complexity hidden inside an n-qubit system. There are n 2 to the n possible bit configurations, but the state could be in a superposition of all of them at once, right? So that's something to keep in mind. So in general, an n-qubit system okay? So an n-qubit system is a superposition where for every possible bit vector, I have a corresponding amplitude, right? The state itself is quite complicated for us to describe. I cannot write it down with less than 2 to the n numbers. Okay? Does it make sense? Of course, it doesn't make many, it doesn't mean I can access all of these numbers. There are lots of other constraints on how I can operate them. But the description of the state is already complicated. Okay? Any questions about that? I should warn you that this is where most of popular science kind of, goes wrong. Right at the first step, they say, okay, now I have 2 to the n possibilities represented in one single n-qubit systems, and hence I have I'm exponentially more powerful than classical systems. That's really ridiculously wrong. But you see that repeated many, many times. Okay? So even though the state has this much description complexity, it's not like I can access them freely. There are lots of other constraints. We have this weird, strong linearity, right? The whole trick is in figuring out how to take advantage of the complexity of the state, as constrained by the operations we are allowed to perform. Okay, so you have to play these two things together. Okay, so we know what a multi-qubit system is. Now, let's see how gates operate on multi-qubits. Okay, and once again, we will take some guesses, and it turns out that our guesses will be correct for the most part, right? And I'll draw some simple things where our guesses will be correct, and then we'll see what happens when they're not. Okay, so I'm going to draw a 2 qubits circuit, more or less, and that's going to be the following. Okay, so I have a 2 qubit state, 2 photons. Imagine I do a quantum knot on the first and nothing on the second photon. Okay, so overall, this is my new circuit. The blue box is my new circuit. I'm operating on 2 qubits. The first qubit is going through a quantum NOT gate. The second qubit, nothing's happening to it. Okay, so what is this gate or circuit now? Because it's operating on 2 things, we call it a circuit. We'll define it formally soon. But what is it going to do, right? But what is it? I mean, we want to know what's the input-output behavior, right? If I send in a qubit in state, remember it's a 2 qubit state, right? So there are 4 possibilities in describing the state. It's alpha 0 0 times 0 0 plus alpha 1 0 times 1 0 plus alpha 0 1 times 0 1 plus alpha 1 1 times 1 1. And then I get a psi out. But what is this? Okay. Any guesses on what I should get? It's actually a little bit complicated to take an outright guess, but we can go back to the first principles, right? To figure out what a circuit, quantum circuit, or a quantum gate does on multiple bits, I need to figure out what it does on the basis vectors. If I know that, I can extend it to all possible states by linearity. Okay, so I need to figure out what happens under 0 0. So let me call this circuit C3. So what should C3 be? If I apply the circuit on 0 0 Any guesses on what the output should be? Yeah? 1, 0, right? Because the first qubit is going through quantum knot, so it should get flipped. The second one is going straight through. Okay? If I send 1, 0, I should get 0, 0. If I send in 0, 1, I should get 1, 1. If I send in 1, 1, I should get 0, 1. Okay? So I know exactly what this circuit does. On any input, which is of this form, alpha 0, 0 times 0, 0, and so on, it gives me bilinearity okay? And we know exactly what these things are. All right? You'll do these things kind of, step by step for the first few circuits, and then we will see how to skip some of these calculations. Okay? Now, this is the way you would describe the circuit in terms of how it operates on the individual basis vectors and then using linearity, right? But we also said every circuit, every gate corresponds to a linear transformation, right? So how do I figure out the matrix corresponding to C3? If I have alpha 0, 0, alpha 1, 0, alpha 0, 1, alpha 1, 1. Now my matrix is a 4 by 4 matrix because there are, it's operating on 4-dimensional vectors. And if my input is the vector alpha 0, 0, alpha 1, 0, 0, 1, 1, 1, my output is what? The coefficient of 0, 0 is 1, 0, right? The coefficient of 1, 0 is 0, 0. This is alpha 1, 1. This is alpha 0, 1. Okay? So the matrix can be, is not arbitrary. You need to fix on an order for writing down the coordinates, right? So it's a linear transformation, but if I change the order in which I write down the coordinates, the matrix would also change, which makes sense. And the order that we are fixing on is basically, I'm going to write down 0, 0 first, 1, 0, 0, 1, and 1, 1. Okay, if I change this order, the matrix would also change. Okay, but what matrix would give me this operation? When I input the vector in blue, I should get as output the vector in cyan. Any guesses? No? Yes? Yeah?
What's the one, the quantum that corresponds to the code?
Yeah. So basically what it's doing, right? It's kind of flipping the first two coordinates, right? It's swapping the first two coordinates and then swapping the last two coordinates. And it's not mixing across the first half and the second half, right? It makes intuitive sense because my circuit is sending the first gate as is sending the first photon as is sending the second photon as is, but it's not kind of mixing stuff yet. Okay? And there's a name for it in physics. It's called entanglement, but we'll talk about that later. All right. Now, so my claim is that this is actually this is a matrix corresponding to C3. You can check it. Okay, so if I multiply the first row with the vector, I get exactly alpha 1, 0, and so on. Okay, and you can kind of notice a pattern here. So what's the pattern in this matrix? Do you notice a pattern in this matrix? What does this correspond to? Oops. The Q0 gate, right? So in some sense, we can think of it as a block matrix where I have Q0 here, 0 here, 0 here, Q0 here. Okay? Right? And this is not something, again, is that you're going to be tested on, but for some calculations, it's helpful to think of it as the tensor product of the matrix which is 0, 1, 1, 0 and identity. Okay, so what's the tensor product? Tensor product takes two matrices and kind of replicates the first matrix in the locations of the second matrix. Okay, so let's say I have two matrices. Here I'm going to do, this is A tensored with B. And let's say B is a 2 by 2 matrix. So I have B0, 0 and 0, 1, B1, 0, B1, 1. So let's say these are my entries of the B matrix. Then A tensor this is effectively okay, so I build a bigger matrix by replacing each entry in my B matrix with essentially a copy of the A matrix. Okay, so either I can use first principles to compute the matrix, or we'll see some tensor product rules to compute them. Okay, if the tensor product thing is too confusing, you can forget about that. You can always work from first principles, at least for the things that we are going to discuss. Okay, so just compute what it does on the basis vectors and then extend it by linearity to everything else. Okay, any questions? No? All right. So today we saw three circuits already, quantum circuits. The quantum knot, the Hadamard gate, and the simple combination C3, which we call. Okay. And as we will see, there is not much more in defining full-blown quantum circuits, right? But we need to decide or formulate how they operate, not just on 2-bit qubit systems, but on n-bit qubit systems, on n-qubit systems, and so on. Okay? And we'll talk about that in our last class on Wednesday. All right? So I'll see you all on Wednesday. And remember, the exam is next Monday from 8 a.m. to 10 a.m. All right, it's early in the morning, but we have to follow the university schedule. Okay. Question? Sorry? Wait, is December 9th? Oh, yeah, Tuesday. Sorry, December 9th is a Tuesday. Yes. Yeah, December 9th is a Tuesday. Yeah. The date is December 9th. Yeah. Okay.